Hello, my name is Art Krener, and I am going to give a talk on manifold reconstruction and the technique we call it is Simplicial Nonlinear Principal Component Analysis. Before I start, I want to thank Boumediene Hamzy and the other organizers for putting together this very interesting meeting. So let's get right to it. This is work that I did a few years back with a postdoc named Thomas Hunt, and all the good stuff in it is due to Tom, and all the bad stuff in it is due to me. So I hope you can see the slides. We were at the Naval Postgraduate School when we did it, and we had NSF support. So here's the problem. We want to reconstruct a manifold from a point cloud that falls on the manifold. So we have a point cloud in a high dimensional space. We typically take dimension 50 for the ambient space. The manifold itself, this little n, is going to be 2 for us. The algorithm generalizes to higher dimensions, but we haven't implemented it in code yet. So we start with this point cloud here on a sphere or on a torus. And our goal is to construct a simplicial complex, in this case a triangulation, that approximates the point cloud. And hopefully we can do things like compute the homology of the manifold from the simplicial homology of the simplicial approximation. So our data is a point cloud. We typically take on the order of 10,000 data points, and our output is a simplicial approximation to a two-dimensional manifold. So that approximation consists of triangles, edges, and vertices. Not every data point is going to be a vertex in our triangulation. We want to reduce the number of data points that are in the triangulation, so we're actually doing a data reduction method. So here are the resulting vertices, here are the edges, and here are the triangles. So we compare this with PCA, principal component analysis. We have a set of sample points in a high dimensional ambient space, and we construct the empirical covariance matrix. We first normalize so that the mean of the data is 0, and then construct the empirical covariance. And then the principal eigenvalues and eigenvectors of P are what we're interested in. So we're assuming the eigenvalues are ordered. They're all non-negative. They ordered from 1 to cap n, lambda cap n, lambda 1 to lambda cap n. And we assume at some point there's a spectral gap. The nth eigenvalue is considerably larger than the n plus first eigenvalue. So then we would say that the n-dimensional linear space spanned by the first n eigenvectors is a pretty good approximation to the data. Now, PCA works great if the data is linear, but if the data is curved, as in the case of the sphere and the torus that I showed you before, PCA doesn't give a very good approximation. So we're developing a method called Simplicial Nonlinear Principal Component Analysis. Data points lie on a high dimensional space but fall on a two-dimensional manifold. We're assuming there's low noise in the data, although we can tolerate a little bit of noise. The algorithm is local, and so it's easily parallelizable. The algorithm consists of 2 stages. One we call the advancing front stage, and the other we call the seam sewing stage. So in the advancing front stage, we have some existing triangles in our triangulation, and we're trying to construct a new triangle. Okay. So we choose an edge. This is the active edge. It bounds only one triangle. We want to find a vertex out here and add a second triangle using that edge. So by some algorithm, we compute an ideal location for that new vertex. It may not be a data point, so to keep consistent with the data, we nudge it to the nearest data point. and then we get the triangle, the new triangle. We keep on doing this over and over again. So I'm going to go to show you this algorithm in action. We're in 50-dimensional space. The data lies on a torus in 3 dimensions in that ambient space. And we're going to run it. And in real time, here's the algorithm proceeding. It's constructing new triangles adjacent to old triangles. And they kind of snake around. It's kind of a ribbon that snakes around the torus. And it leaves some gaps. The ribbons, parallel ribbons may have gaps between them. But that's the first part of the algorithm, the advancing front stage. So we'll come back to this later in the talk and see what we came up with. Okay. Then we follow the advancing front stage by the seam sewing stage, which starts with a triangulation from the advancing front stage. And we pick an active front edge, an edge that only bounds one triangle. And we try to find among the existing vertices a way to complete that, put another triangle in that uses that edge. So that tends to sew up the gaps between the ribbon-like construction from the advancing front stage. Now, locally, a manifold resembles tangent space. And so the tangent space at a point X, the manifold is described by a map from a region in R2 to Rn. And locally, around some point S1 bar, S2 bar, the tangent space is spanned by these 2 directions, the 2 tangent vectors. So the manifold locally looks like this 2-dimensional affine space, but as we get away from this point X of S1 bar, S2 bar, it curves away. So in principle, sorry that I went backwards. So the key thing is how fast it's curving, it's a manifold curving away from its tangent space. At this point here, there's quite a bit of curvature. This is a 1-dimensional manifold. And at this point here, there's a lot of curvature. But at most of these points along here, there's little curvature. So the tangent line pretty well approximates the manifold in this region and in this region. Now, I keep on pressing the wrong button. I apologize. In 2 dimensions, if we have a 2-dimensional manifold, then there are 2 directions of principal curvature. One direction is the direction in which the manifold is most curved, and the other is the direction in which the manifold is least curved. And these 2 principal curvatures, the directions associated with these principal curvatures are orthogonal. So here's how we do it. We form something called the empirical direction covariance matrix. This is the analog of PCA, but we do it with normalized unit vectors. So this denominator here makes these 2 vectors in the numerator, the outer product of these 2 vectors in the numerator, into unit vectors. So this is a direction. This is not a tangent vector. It's a unit vector, which we think of as a direction. We're in some neighborhood around this point V1, and we're looking at all the other points in this neighborhood. And for each of those points, we calculate this quantity and sum them up over the neighborhood. So here are these directions, and we define the neighborhood as a unit, as a ball of radius r sub s, or we could define the neighborhood as a fixed number of nearest points. But we'll take the ball of rs, make some of the analysis simpler. So this normalization denominator gives equal weight to nearby points and to far-by points in this directional covariance. In a standard covariance without this normalization, the far points dominate the covariance. We don't want the far points to dominate. We want the nearby points to dominate, or at least be taken into account. The numerical rank of this P1 is approximation to the dimension of the tangent space through V1. And since we're in 2 dimensions, the dominant eigenvalues, and when we expand them in a series in the search radius, the radius of the ball, start with the number 1/2. If we were in an n-dimensional manifold, it would be 1/n. So this is a way of, given data, this is a way of estimating the dimension of the data. The corresponding eigenvectors approximately span the tangent space at V1, and they're nearly aligned with the directions of principal curvature. So we choose a regularizing parameter, typically of size mu equals 10 to the minus 6, and we form the inverse matrix, P1 plus mu I. This regularizes and allows this quantity to have an inverse, and we form Q1. Now this inverse is a metric. It's a way of measuring differences. Q1 it has the dimensions of a metric. It's a way of measuring distances. So the distance of a point, of a vector, the norm of a point in this Q1 metric is X transpose Q1X, take the square root of that. So when we set that equal to a constant C, we assume V1 is 0, then we get n-dimensional ellipsoids. So n is the ambient direction of the space, so that's 50-dimensional. But these ellipsoids are pancakes. They're very flat. And there are only really one or two directions in which they go. So the semi-axes of these ellipsoids are aligned with the eigenvectors of Q1, and the lengths are 1 over the eigenvalues of Q1. And Q1, the eigenvalues of Q1 are essentially the reciprocals of the eigenvalues of P1 plus the regularizing factor mu. So since the first 2 eigenvalues of P1 were 1/2 plus something higher order in the search radius, the first 2 eigenvalues of Q1 are of size 2. And then the higher eigenvalues are of size, the inverse of this regularizing concept. So let's do a little analysis of what we're doing here. If we assume the data points are uniformly distributed according to surface area, and we let the number of data points in a neighborhood of V1 go to infinity, then PV1 is this integral, okay, divided by the surface area of the neighborhood N. This is for a two-dimensional manifold in free space, but the generalization to higher dimensions is pretty straightforward. So here's our two-dimensional manifold. ds is the surface area element, n is the search sphere of radius r sub s, and the data points near V1 are proportional to ds at V1. The number of data points, the density, is proportional to the surface area. So then we get a quadratic form of this form, x transpose mx plus x3. We're assuming the principal directions are x1 and x2, and x3 is the third direction, which we're bending away from. So these are the principal directions. And we normalize V1 to be 0. The tangent space, as I said, corresponds with the x1, x2 plane, and the principal curvatures are the curvatures in the x1 and x2 coordinate directions, essentially. So here are how the eigenvalues of P0 expand in the search radius. So they start with the quantity 1/2, and then there's a much smaller quantity, minus 1 over 32. The search radius is going to be small, so this is a small quantity. Kappa 1 is the first principal curvature squared. Kappa bar is the mean curvature squared. That's the first eigenvalue. Here's the second eigenvalue. Kappa 1 is replaced by kappa 2 in the same expression. The third eigenvalue takes this form. It's quite small because it doesn't have this 1/2 in front of it, and it's of order size the search radius times the curvature, the squares of the three curvatures. So the dominant eigenvalues, vectors of P0 nilly span the tangent space. So they're in the directions x1 and x2, e1 and e2. And here are their deviations. They bend away at search radius squared. Okay. And again, the rate at which they bend away depends on the curvatures. Now we define the inverse of this matrix, and this defines a metric, a way of measuring distances, displacements from V1. And this mu is a regularizer, as I said, it's order 10 to the minus 6. So the smallest eigenvalue of Q at V1 is 2 minus 4 mu. Mu is 10 to the minus 6, so this is negligible, plus something that depends on the curvature. And the next smallest eigenvalue is 2 minus 4 mu, depends on the maximum curvature. Okay, this depends on the minimum curvature. All the other eigenvalues of Q are of order 1 over mu, that is of order 10 to the 6. That's quite large. So displacements from V1 perpendicular to the approximate tangent space are huge. If we're going any direction other than the first two eigendirections, we're going to pay a lot in this metric. So the guiding principles for generating a new triangle, we want to try to find V1, V2 as an active edge, an edge that only bounds one triangle. We want to find a vertex on the other side to construct a second triangle with that edge. And V star is the new edge, or V star is the ideal location for the new edge. So V star, what property should it have? It should lie near the tangent spaces through V1 and V2. And V star minus V1 and V star minus V2 should lie in directions of mild curvature from the underlying manifold. The metric Q measures the curvatures at V1. Q at V1 and Q at V2 measures the curvatures at those points. So we build these two metrics. If X is not in the tangent space through V1, this quantity is very large. If it's not in the tangent space to V2, the corresponding quantity is very large. If X lies near the intersection of those two tangent spaces, these quantities are relatively small. So the active front edges, V1 and V2, we want to find the midpoint of that edge and the outward normal. We want to put the new vertex on the other side. So we solve a quadratic programming problem. We compute these two metrics. We find the X star that it forms the Ardman of the ideal location for the new point from the point of view of Q1. Why do we favor Q1? Well, we don't favor Q1. We put in an isosceles constraint that the distance X is from V1 as measured by Q1, the squared distance is equal to the squared distance that X is from V2 as measured by Q2. Now we don't want any skinny triangles, so we add this equilateral constraint that says X should be a certain distance from the midpoint. And this distance is the distance that if it were achieved, it would be an equilateral triangle in the standard Euclidean metric. We also want X on the other side, away from the existing triangle, So that's what this advancing front constraint adds. And that gives us an ideal location, X star. We nudge that to the nearest data point in the local metric at X star. We can compute metrics anywhere. We don't have to compute metrics at a vertex. At any point X, we can form those directional covariances and so on. So here's the new vertex angle. The angle between the two tangent spaces is 24 degrees. So the tangent space at X at V1 and the tangent space at V2 make an angle of 24 degrees with each other. The blue ellipses are the intersections of, these are distances from V1 as measured by Q1. These are square distances from V2 as measured by Q2. So we're going to let them go, 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 go. At some point, they satisfy the equilateral constraint. At that point, that is the intersection point. So there's our new triangle in green. Now, the manifold curves away from the tangent space most quickly in the directions of maximum curvature. So if lambda is huge, an eigenvalue of Q1 is huge, then points outside the tangent space are very far from V1 as measured in the metric Q1. If we're talking about 2 points in the approximate tangent space are equidistant from V1 in the Euclidean metric. So minimizer that we're getting lies near both tangent spaces through V1 and V2 and favors the balance of X star minus V1 and X star minus V2 in the directions of mild curvature. So should we accept this new triangle? Well, it might conflict with the existing triangle. It might overlap or intersect an existing triangle. So we have a little test here to measure whether it does. I'm not going to go into the details. It's fairly straightforward. Now, the advancing front stage produces an incomplete triangulation of the manifold. The seam sewing stage completes the triangulation. So if we have an edge that has only one triangle associated to it, we call that an active edge. Then we find an existing front edge vertex, V3, by minimizing, by taking the argument of V minus V1 in the Q1 metric and V minus V2 in the Q2 metric. So this search is not over all points X, it's only over data points V. So existing edge, it's only over existing vertices V, rather. So it's a finite search. And we do when we check also after we do that, we check that we're not conflicting with an existing triangle. Okay, so synthetic data sets. Here's the results of our algorithm. We're going to generate points distributed uniformly with respect to surface area. We're going to form these point clouds in 50-dimensional space. We're going to embed them, randomly embed this 3-dimensional space that contains our data points into 50-dimensional space, and we're not going to tell the algorithm what the embedding is. The algorithm has to find out for itself. So we plot those vertices. So here is the results for a torus. The torus has radii 1 and 4. Okay. And I hope you can see this. The resulting triangulation will have 681 triangles. There's 10,000 data points, but we're only going to use 342 as vertices. And the characteristic length of an edge, this is the typical length of an edge, is going to be 0.75. So the maximum distance of a data point from the resulting triangulation is 0.10 as compared with the characteristic length of 0.75. So they're fairly close. The average distance is much closer, and the square distance is much closer. 10,000 data points. Here's the results after the advancing front edge, and you see we have these gaps here, and here, that we need to fill in. And that's what the seam sewing stage does. So now we have 681 triangles. The number of vertices has stayed the same, and there is the other data. Now, a triangle, the manifold can be a manifold with boundary. The algorithm works well. So here's a creased sheet. So it's a folded piece of paper, and we're going to get it. Again, it's 10,000 data points, and we're going to get an approximation with 1,289 triangles, 669 vertices, and a characteristic length, in this case, 0.35. You can see the length of the sheet is approximately 10 in this direction and 12 in this direction. So here's after the advancing front stage, and you see these seams that need to be sewed up, and the seam sewing does well. So the maximum distance of a data point to this triangulation is 0.1, as compared with the dimensions of the figure are basically 12 by 10. So that's 0.1 is quite small. Here's a standard example, which is a piece of cake for us. It's the Swiss roll. This gives things like PCA a lot of trouble. If you did a PCA on this, you'd get a flat plane cutting through the roll. You'd lose all the information about the roll. So again, 10,000 data points. After this advancing front stage and after the seam sewing stage. Okay. There are some little triangles that we don't like. They're kind of skinny triangles here, but most of the triangles are close to being equilateral in the standard metric. Here is a non-standard problem. We're going to take a sheet of data and we're going to twist it through 6 dimensions. So this is a flat sheet of paper twisted through 6-dimensional space. So here, if we project down onto the first 3 dimensions, if we take x1, x2, and x3, here's what the projection looks like of the data. And here's what the resulting triangulation looks like, restricted to those 3 data. If we go into x2 through x4, we get this triangulation. And here's x3 through x5. And finally, x4 through x6. So even though most of the problems that I showed was a 2-dimensional manifold embedded in 3-dimensional space, then embedded randomly in 50-dimensional space, you can see this algorithm is perfectly capable of handling 2-dimensional manifolds that twist through 6, 8, 10 dimensions. Okay, finally, one real data set. We got this from the International Journal of Robotics Research. This is a Ford Campus Vision LiDAR data set. Okay. It's an urban scene, 2,100 points. It has almost 20,000 vertices. And when we do the algorithm, and 30,000 triangles. Our algorithm can be restarted. I didn't mention this, but if the algorithm runs and you're not satisfied with the results, you can go to some place where the algorithm hasn't put simplices in and restart the algorithm. Now this urban scene contains trees, billboard, van, and true and spurious holes in the data. So here is the data, the LiDAR data, or the forward thing. Okay. And here is our algorithm, what our algorithm does to it. Okay. So it triangulates the real data pretty well. We'd probably restart the algorithm over here in this place, but for these data to get triangulations there. Okay. So that was after the advancing front stage, and here's after the scene sewing stage, and all those little gaps are sewed up. So I wish I could take questions from you, but before I go, I'd like to go back to the MATLAB program that was running and see what happened. Okay. So here is the, let me see if I can expand it. Anyhow, let's rotate it. Here, this is what I want. So I'm rotating it. This is the triangle. You can see that it looks almost watertight. I don't think it is. I think there's one or two gaps in the triangle. Oh yeah, there's one right there. But it's a pretty good triangulation of the torus. Okay. So thanks for your attention. And if you have any questions about this algorithm, if you want a copy of the code or anything like that, email me ajkrener@nps, Naval Postgraduate School, nps.edu. Thank you for your attention. Bye-bye.